Hi guys, I'm Peter Nguyen, and that is
On.
okay. So our project is called an adaptive headlight. So we have here a 5 volts with the USB cable, and it can supply up to 3 amps current. You can see here that this cable is connected to our breadboard, which has a microcontroller FM4E. This is the accelerometer, and this is a receiver. So this receiver is communicating with this transmitter, which transmitted signals to the receiver. So our project has 3 features. So the first feature is, as you can see, the servo. So our program will tell the accelerometers whether or not the board is tilting from left to right. If the board is tilted to the right, this servo will turn the light to the right. And if the board is tilted to the left, the servo will point to the left. That's our first feature. The second feature we have is the blinks. So this is a wireless controller. Like I mentioned earlier, so this microcontroller will communicate with this receiver. So here we have a switch button. So our programs will have 4 modes. The first mode will, the default mode is off mode, which doesn't turn on anything. The first mode will be turning on the light at 1000 hertz, which is the light will be on continuously. And then second mode is the light blinking at 2 hertz. The third mode is the light blinking at 16 hertz. And the fourth mode, the light will blink at 32 hertz, which is very fast. And third and lastly, the last feature we have is the photoresistor. So the purpose of having the photoresistor right here is to identify whether it is daytime or nighttime. So if this board is riding outside during the daytime, this photoresistor will collect the data in analog values, and this program will read those data. So if it is daytime, this whole system will not work, meaning the program will not be on. But if it's nighttime, which is the whole point of this project, is to turn on the light during nighttime, so it could work. So let's put it to use. Okay. So let's see. So as you can see here, we are in mode 0. The light will be off. So turning this on. So this is mode number 1. You can see here the light turned on at 1000 hertz. Mode number 1. Mode number 2. It blinks at 2 hertz. Mode number 3. I accidentally passed it, but this is mode number 4. It blinks at 32 hertz, which is very fast, if you notice. And it will reset to mode 0, which is turned off. And to show you how the accelerometer works, so if I tilt to the left, the light will turn to the left as I tilt to the left on the board. And if I tilt to the right, the light will turn to the right. Back to normal. So the angle on this is 0 to 180. The middle we set straight, which is the middle, to be 90 degrees. So turn to the right will be 180 degrees. Turn to the left will be 0. That's it. So one interesting thing that we found is that at first when we use the photoresistor, we use a 220 ohms resistor, and we found that when we were collecting data, the analog values, it ranged from about 5,000 to 15,000. So the range is only 10,000, which is very small. So we slowly increase the resistor. The one we use for our project is 1 kilo ohms, which is 5 times greater than the first one that we used. And we found that the range, it goes from 5,000 to 50,000, which is a big difference. And because of that, a big difference of a range, we're able to make our photoresistor more sensitive. So it will detect daytime and nighttime more sensitive. The second problem we came across was we were trying to make the light work from connecting it straight to the pin from the featherboard. We couldn't do that because the pin from the featherboard only supplied up to 15 milliamps, and for the light to work, you need 0.88 amps, which is a large number. So what we did is that we used the PN 2222 transistor. So this transistor acts as a switch. So the light is connected through a transistor and then the power supply, straight from the power supply. So this board will tell the gate to whether open or close. So if the program tells the light to open or the gate to open, this power supply will supply enough amp or current to the light and make it work. And if this program tells the gate to shut off, then the light wouldn't work because there's no current going through. Okay, that's one. So the third problem that we came across in this project is with the transmitter and the receiver. So like I mentioned earlier, we have 4 different modes, but for some reason when we go from mode 2 to mode 3, we just go from blinking at 16 hertz to 32 hertz. There's a lag in between and we couldn't figure out the reason why for that. We tried to touch the wire directly to each other to see if the mode switches from 2 to 3, and we still found the same problem, meaning this switch is not the problem for the reason why it lags. So it must be the problem from the hardware. So that's what's one thing we assume is the problem between mode 2 and mode 3.
The last problem that we have was with the accelerometer communication with the servo. As you turn the board to the left, it would output negative values. How we fixed that is we took the absolute value of it. So after everything was done, turning the board to the left and to the right would yield increasing positive values, which would not work with the servo because we want the servo to go left and right. But if the accelerometer only works in increasing values, the servo would only turn in one direction. So how we fixed that was we set the absolute values of the negative values to 0 and 90 degrees, and all the positive values we set it from 90 to 180 degrees. So overall the system works, but another problem that we found was that since this is really sensitive, even when a person is riding on a straight road, this servo right here would twitch back and forth. So how we fixed that was we limit the servo from moving when the accelerometer is turning from 80 to 100 degrees. So then when you go straight on a road, sometimes you might make slight movement and that would not move the servo.